There are 8 ranges in the proton NMR spectrum that I think you have to know if you want to be a true NMR ninja. Proton NMR is probably the most important spectroscopic tool that you're going to learn in organic chemistry. This is not a video on the theory of how NMR works or how the spectra is obtained, but I do have separate videos linked down below on those topics. When you analyze an NMR is made up of one or more signals, and each signal has one or more peaks within that signal. Every time you analyze an NMR, you have to look at every single signal, and you have to look at its chemical shift, its integration, and its splitting pattern, or its multiplicity. This video will talk about the NMR chemical shift patterns you have to know. I'll have separate videos linked down below on multiplicity and on integration. There are 8 ranges in the proton NMR spectrum that I think you have to know if you want to be a true NMR ninja. I'm going to display those ranges here, and we'll use these 3 molecules on the side to demonstrate which protons would fall into which categories. Play along, see if you can predict which protons will fall in which categories. The first range goes from 0 to 2 parts per million, and it is the regular boring alkyl type proton range. These are hydrogens attached to an sp3 hybridized carbon, where that carbon is not involved in any other type of interesting functional group. You can see the protons highlighted in the structure that would fall into this range. They're typically the end of the alkyl chain protons in that top molecule and in the middle molecule. There might be some other protons that you might have thought should be in the 0 to 2 range, but actually I'm going to suggest that they really fall better into other ranges that we'll talk about here in a minute. The next range goes from 1.5 to 3 parts per million, and this is what I call the alpha proton range. These are hydrogens attached to a carbon that is next to some kind of pi bond. Not a hydrogen directly attached to a pi bond, a hydrogen on a carbon that is next to some kind of pi bond. Very important distinction. You can see that distinction in the structures on the right. The structures have hydrogens that are next to the benzene ring. Those would be alpha type protons. Those are hydrogens on a carbon next to the benzene ring. They also have hydrogens on a carbon next to a carbonyl. That would also be an alpha type proton. Any pi bond would count. Also, hydrogens on a carbon next to an alkene would count as an alpha proton. And you can see other examples of hydrogens on carbons next to carbonyls. These are all alpha type protons. Hydrogens on a carbon next to some kind of pi bond. It doesn't really matter which pi bond it is, but some kind of pi bond. When you draw the fragment for this signal to make your puzzle piece for this molecule, you'll want to include the pi bond, but I would include that little square at the top of the pi bond because you may not know exactly what type of pi bond it's going to be at that time, so you want to leave your possibilities open. I have a separate video that I'll link to down below on how to solve NMR using a puzzle piece strategy, where you take each signal and you build a puzzle piece for that signal and you use it to solve the spectrum of an unknown structure. How do we know which pi bond the alpha protons are going to be next to? Well, there's nothing in the proton NMR that would actually tell you either way. You'll need to use some other context clues. Probably your IR, maybe your carbon NMR, maybe your index of hydrogen efficiency. Those are the types of other clues that you'll look for to figure out what pi bond these alpha protons are next to. Right away, 2 ranges in, we can already see a problem with this analysis. These ranges overlap. How are we supposed to know if a signal falls in that overlap range, if it's an alkyl type proton or if it's an alpha type proton? You'll have to use some other context clues. Maybe you'll need to use the IHD to see if there even is a degree of unsaturation. If there's no degrees of unsaturation, it can't be an alpha proton. You'll have to use your context clues to build out the puzzle piece to see whether it's an alkyl or an alpha type proton. Moving further downfield, the next range you need to know goes from 3 to about 4.5 parts per million, and this is the HCZ region. That's what I call it, HCZ. Hydrogens attached to a carbon that are attached to some kind of heteroatom. Oxygen, nitrogen, bromine, chlorine, fluorine, something like that. These are hydrogens on a carbon next to a heteroatom, not hydrogens directly attached to a heteroatom. Very important distinction. You can see that distinction in the structures. Hydrogens on a carbon next to the oxygen, next to the bromine. These are the HCZ type protons that you want to watch out for in your HNMR. Before we move on to the next range, I want to focus on that boundary right at 3 ppm. If you have a signal that's at 2.9, does that mean it has to be an alpha type proton? And if it's 3.1, it has to be an HCZ proton? No. One of the things about HNMR chemical shift ranges is they're very fuzzy. The boundaries are very fuzzy. It's very possible to have an HCZ proton that's actually like 2.8 ppm. That's not uncommon. You'll need to use your context clues. If you think it's an alpha proton, but there's no IHD, but there is a chlorine in the molecule, then maybe it's an HCZ type proton. You need to consider that these boundary ranges are often fuzzy. The next range goes from 4.5-ish to 6.5-ish parts per million, and this is the vinyl range. These are hydrogens directly attached to a carbon-carbon alkene. Notice the difference between this and the alpha proton range. Alpha protons were next to any pi bond. Vinyl protons are directly attached to an alkene. We can see that in the structure on the right. The hydrogens directly attached to the alkene are the vinyl protons, and they'll be somewhere between 4.5 and 6.5-ish parts per million. The next range, from 7 to 8 parts per million, is everybody's favorite range. It's the Aryl range. These are hydrogens directly attached to a benzene ring. Not hydrogens next to the benzene ring, hydrogens directly attached to the benzene ring. They can be attached to any aromatic ring. But for undergrad organic chemistry, it's almost certainly going to be a benzene ring. And again, we can see the examples in the structure. The hydrogens directly attached to the benzene ring would have signals that appear between 7 and 8 ppm. Aldehydes fall in the range from 9 to 10 parts per million. These are hydrogens directly attached to a carbonyl as part of the aldehyde functional group. We have an example of that in the structure over there. Hydrogen directly attached to that carbonyl is the aldehyde and will appear between 9 and 10 parts per million. The last discrete range goes from 10 and above, 10 to 12-ish parts per million. These are the carboxylic acid protons. The proton on the hydroxy group of the carboxylic acid will have a signal that is above 10 parts per million. It will often be very broad as opposed to very sharp signals that you would typically see in other ranges. Sometimes that signal is so broad that it gets so flat that you don't even see it at all. It might not appear at all. These are all the discrete ranges in a proton NMR that I think you need to know to be an OChemNinja for proton NMR. But earlier I told you there were 8 ranges I thought you should know. The last range that we haven't covered are hydrogens directly attached to a heteroatom, OH or NH type protons, alcohols, amines, amides, those types of protons. Where do they show up in an NMR? They show up anywhere from 0 to 12 parts per million. If they show up at all, and this is very frustrating for proton NMR. Protons, that hydrogen bond, that electron density around that hydrogen is variable depending on the solvent, depending on the strength of the hydrogen bonds, and that really changes the chemical shift of those protons. And because of the hydrogen bonding, the signals will often be broad. That's one way to tell them apart from regular proton signals. They might be so broad that they don't show up at all. It's very frustrating. You're going to be going through your analysis and you're going to be calling something an alpha proton, but it can't be an alpha proton. There's no index of hydrogen deficiency. Something is just not right. In that case, consider the fact that it might be a hydrogen bonding proton, maybe an OH or an NH proton. Cross-reference with your IR to see if you have an OH or an NH proton that you need to account for. There you go. Those are the proton chemical shift ranges that you have to know if you want to conquer organic chemistry proton NMR analysis.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. Help spread the word around the country. As always, don't forget to like and subscribe.